So, am I audible with you all here?
Yes, sir.
Yes, sir.
Okay. So, okay, let us start what we have started in the previous class here. So, if we summarize here what we have discussed in the previous class here, then basically we try to build up the basic understanding of the probability concepts here. And then subsequent classes here, we have gone for some basic understanding, further understanding of probabilities, and the subsequently classification of events. Then we have tried to correlate those events here with the uncertainties in terms of their associated probabilities here. This was our basic understanding to define the probabilities here. And in the previous class here, if you remember, we have talked for the types of probabilities, also especially the conditional probabilities here, where we talk some types of events here, and then we have defined their associated probabilities here. So this was our basic understanding of whole events here, and now we are going to discuss in today's class one of the very important aspects of probabilities, where a lot of discussion or buzz happened related to the machine learning. So many of you are aware about it. Okay, not precisely to the point here, but you can say in a very qualitative way, you people have some understanding. Okay, so before we move ahead here, comes to that points here. So let us discuss quickly. There are two more points here. Then we will go through the base theorem here, and then we talk about this machine learning, how it could be useful here. And prior to that, we will try to understand how this base theorem is so important here. What is the fundamental behind all those arguments people put forward here? So, okay, let us talk one specific type of events here. This is the independence of events here. We have discussed subsequently at the many places here through our discussion. So let us put it here based on the previous understanding of conditional probabilities here, as well as the independence of events which we have discussed earlier here. So we are slightly tuning this independence of events here with respect to the its association with the conditional probabilities aspects here. Okay, so here we are defining that probability of So here we are defining that the probability of an event A is the same regardless of whether or not B occur here. Correct? So in general, here what we are defining in this situation, P A by B. So what it means, the moment we say A slash B here in the aspects of probabilities, then we define we are interested to find out the probability of A with respect to the given information here corresponding to the B, correct? This is our understanding in the conditional probabilities we have understood here. So here, very interestingly, if you remember our previous discussion of conditional probabilities here, then we have written P, A by B is equal to P, A and B divided by the probability of B here. But here we are writing probability of A given B is equal to the probability of A. So this equation holds true here in those cases where we clearly state that the occurrence of events are totally independent in the nature here. Means if I'm going to define an event here, it will be totally different, or its outcome is not going to be influenced by the previous outcome here. So this will be totally different here. So the multiplication rule for the two independent events, if we move ahead further, so first important conclusion which we draws here at this point here is this one here. First, And second, if we further extend it in case of multiplication rule here, so as the events are independent in the nature, then we could write their A and B is equal to probability of B multiplied with the probability of A here. Correct? So thus we see that if two events are independent, the probability of their joint occurrence is equal to the product of the probabilities of their individual occurrence here. And because they are not dependent here. There's no dependency in the successive events here which are happening here. So if you summarize all these here, then probability of A given B is equal to the probability of A at the first place. Second, probability of B given A is equal to the probability of B and B, A and B, where probability of A and B will be equal to the product of given probability of A and the probability of B here. So this is just some conclusion, or you can say based on the observation here, so we have drawn these conclusions here, and we try to correlate it with the conditional probabilities aspects here. Correct. Now we are little bit moving ahead further. One more. I think someone need to unmute himself or herself here. Okay. We're just creating a continuous disturbance to the others. Okay. So it is again just a reminder here, when you will join the meeting here, you need to keep yourself unmute throughout the meeting here. And whenever you need to ask something, or in the discussion it is uh, requested that you need to speak something here, then at that time you say just unmute yourself and then uh, talk here, and again further go for the mute. Okay, so this is just a protocol, you need to follow it here, so it will help the others here. Okay, so laws of total probabilities here. So here what we are doing, let the events b1, b2 and bn, here this is the partition of the finite sample space. So what is the sample space? Could anyone?
Sir, the total number of outcomes.
It's a collection. Okay,
Yes,
what you say, that's correct, correct. So it is the collection of total outcomes here, corresponding to any experiments here, correct? So based on that, we define the sample space. So the moment we define the sample space, it means all the possible outcomes have already been considered. There is nothing left out of this collection box here. So we can say sample space here. Everything is part of it here. So here, what we are defining, so let the events B1, B2, Bn partition the finite discrete sample space as here. So for example, here corresponding to sample space, we have partitioned it into the n events here. For example, if I'm going to toss a coin here, so its sample space will include the two possibility head and tail, correct? So out of these two possibilities, one event could be the head, another event could be the tail here. So in case of tossing a coin, I could define a sample space where it could consider the two events here, head and tail here. Subsequently, in the general form, we have defined a sample space here where there are n events here, which are possibilities here. So for an experiment, and let A be an event defined on S here. So here we are trying to define an event A, and how this event is defined, probability of A is equal to probability of A and S here, sample space S here. So we are going for the AND operation with sample space S. So as S represents complete completely by this n number of events partition here, so I could write this sample space as here at this place as like this, correct? What is written here, this is just a representation corresponding to the sample space as here. The A intersection S, so I just A intersection, and this is the part equivalent representation in case of sample space S here. Now, once we have this equation here, so little bit further mathematical operation we have applied here, and corresponding to this A event A here, I have gone for the further interaction, or you can say operation, with different events B1, B2, and so on here. So this equation could also be represented like this form here. Once we have the equation in this form here, now I can apply some mathematical axiom operations here, and then I can comes to this form here, as probability of this association is in terms of their union in between here, you can see. So once we go for it here, it would be replaced by the plus sign here. Okay, so P A intersection B B1 plus, and so on here. We can move ahead here. The moment
Sir,
we have
sir, how did we jump from union to plus everywhere?
actually in the basic probabilities discussion here, we have not gone very depth detail here, but if we go to the probabilities properties here, okay, there are certain properties here. Based on those property, we could interconvert here. Okay.
Okay.
So if you go through the book here, you will find these properties. If you are not able to find it here, just let me know. I can we can have a discussion. Because right now I don't have the content here, so to show in the slide here. Okay. Otherwise, this is as per the
Okay, sir.
properties of the probabilities here. We could come to this one here, from intersection and
Sir,
this.
which book, sir? The Shom's outline or the MIT one?
So anyone, I think, so probability. I don't remember exactly which one book I refer here, but I think you can find. If you're not able to find it here in the textbook here, okay. So just let me know. I could
Hmm.
share it here with the complete reference.
Okay, thank you, sir.
No issue. Okay. This is the property. And the properties, if you see, you can say the Venn diagram and other things. If you go through it here, you can find this kinds of proof is also there. Okay. So here, based on this property, we could comes to from here to this one here. If you're not able to find it here, you can say it here. I will show the complete reference here. No issue. This is property. So once we have in this form here, probability of A intersection B1 here. Now I have a thoughts to apply this property with its associated conditional probabilities here. Correct? So how I could interlink here the probability of A given B1 into probability of B1 here. Correct? So how this is coming? I think if you remember the conditional probabilities equations here, A by B1, just previous one here. So what is written here? I think no, this is conditional probabilities. Yes, here. So when you talk about the conditional probabilities here, we have written in this form, and the same has been written this. We are talking a reference from here. Probability of A given B is equal to probability of A intersection B divided by the probability of B, and probability of B given A is equal to the probability of A intersection B, or A and B, divided by the probability of A here. So if one is intersection B form, I could represent either of the equations here. Okay, yes, come to the point here. So what we have done, probability of A intersection B, I just arranged in mathematically here, and we have written in terms of their associated the conditional probabilities here. So for the first term here, and similarly I could expand it just like this we have done in case of first term. I could go for the second terms too here. Probability of A, this could be written as probability of A given B2 into multiplied by the probability of the B2 here, correct? So on, if I can extend it up to the nth events here. So if I summarize it here, here, then I can say in the summation form I could write where I is equal to 1 to the n here, and this probability of A given Bi here into probability of Bi. So you can refer corresponding to the first term here B1 is appearing and its associated multiplication is also probability of B1 here. So whatever the value I will consider here, if I is equal to 1, so here B1 and this place also B1, here B1 and then here B1 here. Subsequently, if we take I is equal to 2, so it will be B2 and at this place and the B2 at this second place 2 here. So I could represent the entire terms values here. Right? Now, so based on this properties which you observed here, this is called as a laws of total probabilities here. So PA. So here the important inference is if I am interested to go for a probability of any events A here. So this could be also find out here with the associated conditional probabilities and the multiplication of the events associated events to here with respect to the. And here the important conclusion is we are trying to find out the probability of A corresponding to the given B here. Correct? So this is just mathematical terms here. It may not be so very clear to you at this stage here, but once we go to the problem statement here, solve the problem here, this thing will be more and more clear to you here.
Sir.
So for time being, if you could refer it here, so this is related to the probability of A, and this is the summation. So this summation will gives the total aspects here, so or you can say completeness here. So this way we define this equation here or represent this equation here as a total probabilities here. So which will
Sir.
consider all the aspects here with respect to the an event B. We are trying to infer the information for an event A here. So this is the basic understanding or some sort of this information will need here in case of Bayes probabilities here or Bayesian probabilities here. So before we move on to the Bayesian probabilities here, in the starting of class here, we have discussed about this is the fundamentals for the machine learning here. So what do people have the understanding about the machine learning? Just very qualitatively here, you can speak or you can write in the chat box. I think CSC, EC, DSAI is all the three branches are here. So I think some sort of understanding you have. Nope. Machine behaves as per past experience or fact taught to him. Okay, good. This is Himansu. And
Sir,
question
the
says the previous
recommendations.
data.
Sir, the
Mhm.
recommendations we get on various apps, it collects the data we have used. Means if we use any app, it collects the data which video we see frequently, and it uses that analysis and gives us the new references using this method.
Okay. So you people think here you people don't need the AI or machine aspects here. So here said machine learning is an AI that learn things on its own using previous inputs here. Machine learning is based on AI. Okay. Any other data? Any other input here?
The machine learning is basically used to like handle a large amount of data uh, so that we can use data analysis and then quantify basically quantify the data to get some output.
Okay, quantify the data here. So means you are saying the analysis of the data. Based on the analysis of data, we are trying to predict. Okay,
Yeah.
good, good. Anyone else? Machine learning is based on AI. That's Vikalp. Okay. So machine learning is a subset of AI. So artificial intelligence is very broad domain here, and machine learning is just a small segment of that AI. Okay. Okay. Let us move on based on your understanding here. So now you can conclude here what people have presented here. So once we talk about the machine learning here, so based on the previous data here, we are trying to articulate something here which is may happen in the future, which actually have not happened here. Okay, and simultaneously, the more and more data analysis will give us the more and more clear picture here in the here, and all this is based on the algorithm here. What we are I'm going to develop here, or how I'm going to extract the information, or like how could I correlated with the past experiences here, because what is we have observed in the past here, based on that we are trying to articulate what may happen in the future here. So this is our basic understanding for the machine learning and how we are going to use it here. So now let us understand the Bayesian probabilities here, and then we'll try to correlate at what point, what is the property of Bayesian is so useful here, which work as a foundation here for the machine learning here. We are not going to discuss the machine learning in this course here. We are just trying to correlate what could be the possible application here corresponding to this Bayesian probabilities. And there are many other areas where we could apply these concepts here, or people have used these things here. Okay, so with this, I'm moving ahead here. So once we talk about the probabilities here, so as we discuss probabilities only related to the uncertainties involved, we're at the first place here. Okay, and when we are trying to define the probabilities here based on the frequency of that event or occurrence of that events here means based on this past record here, we are trying to assign some probabilities here, or just giving the some number between 0 to 1 here, and as we have defined here, we call it this number as an associated probability corresponding to that event here. So once we say this Bayesian probability here, it's a measure of a state of knowledge. uh, it quantifies uncertainties, allow us to reason using uncertain statements here. So once we solve some of the problem here, then this statement will be more clear to you. What it states, it quantifies uncertainties here. What is uncertainty at the first place here? Once we move ahead through the analysis here, now we will have the more clear picture, correct? Related to the same events here or the same experiments here which just had happened. At the first place, we are not so concrete to give the output here statement here, but once we have gone for some analysis of data here, we could say, no, this is, it seems at the first place is not the actual picture. This could be a slight variation here. The Bayesian model is continuously updated as more data is acquired here. So this is correct. The more data you have means more the past experience here which you have with any events here, then the more certainty or with more accuracy you could predict the behavior here. So this is the related to the our common understanding also here, a common intuition here. If I know some person here from a long span of time here, then I can predict his behavior more accurately here. For example, if someone asks about you, what is the behavior of a person here, or your 12th standard friend here, so if you have spent or very long, maybe someone from 1 to 12 or someone from 6 to 12 here or 11 12 here, so based on that span of time you have shared here, you can predict what would be his behavior. So means past experience you are counting here. And subsequently, if I asked here regarding your BTech friends here, people have just met a few days ago here, hardly you can say few months happened with you all here. So some sort of a small discussion. If someone asks how you could judge your friend here or how your friends are here, so it will not be so accurate here, accurate prediction from your side related to your friend's behavior here. So this way, similarly, the machine or whatever people are trying to articulate here, this is also related with the past behavior, past experience here. Whatever the data we have available in the past year, based on that data, we are trying to predict what it could be here. And this Bayesian work is a base model here in this whole exercise here. So now we will go for the further mathematical aspects of Bayesian here, and then we'll try to correlate it with the practical aspects here. So it is also known as the inverse probabilities here. Here, correct, because we are going to use the conditional probabilities here. We will observe mathematical terms here. Then we can say probabilities can be revised when the new information pertaining to a random experiment is obtained here. What I was trying to say here, based on the new information, our first impression would going to be revised here. Correct. So, for example, if you have given some remark related to your friends here, based on your normal discussion here, but if some past information related to his family background, his academic background, or if his extracurricular activities are known to you here, then your opinion would change about him. Correct. So this is the additional information which you have with yourself is going to help you in the better prediction here. So one of the important application of the conditional probabilities is the computation of unknown probabilities on the basis of information supplied by the experiments or past here. What we will say, probability of A we are interested to find corresponding to the given B here. So one event is already happened. Based on that information of event B, we are trying to find out the probability of event A here. So this is mathematical terms here. We have already observed these things here. That is, application of the result of probability theory involves estimating unknown probabilities, making decision of new sample information here. So this will be more clear to you once we solve the problem. So Bayes theorem shows, in a nutshell, if I conclude here, shows the relationship between a conditional probability and its inverse here. Okay. So here, in case of conditional probabilities, we have already discussed these two statements here. We are familiar, correct? So probability of A given A and B is equal to probability of B multiplied with the probability of A given B, and this is probability of A intersection B, could also be written probability of A multiplied with the probability of B given A here. And from where this is coming, if I could bring this term here in the this side in the denominator here, because you could see probability of A given B is equal to the probability of A and B divided by the probability of B, and at this side probability of B given A is equal to probability of A and B divided by the probability of A. So this is our conditional probabilities rule here, which we have already learned and discussed in the previous lecture. So just the mathematical arrangement of those two mathematical equations here, and based on those two mathematical equation understanding, we have simply rearranged them here. Now we can see both are equating in terms of probability of A and B here, correct? So once we have this information, probability A and B and probability of A and B here, now I could equate these two equations, correct? As these two equations left hand side is equal here, so I could equate the right hand side quantity in both the cases here. So once I equated both sides here, so then we comes to the very important equations here, and this equation is the foundation for the machine learning. Okay, and how it is helping it we will learn with our continuous discussion here. So from the conditional probabilities properties known to us here, after just arranging the terms slightly here, I could equate the right hand side of the both the expression, and from here I could write probability of A given B. So just try to understand what is said mathematically, then we will see. Probability of A given B, we are interested to find out, it would be equal to the probability of B given A multiplied by the probability of A divided by the probability of B here. So what it means here, what is the association here, correct? Then how this is the information is going to be useful in estimating what could happen in the future here, or you can say this is the past information available with us here. Based on the past art information, we are trying to make a inference about the probabilities or hypothesis here, or more precisely we can say the hypothesis here, because this is just an inference based on the associated probabilities or hypothesis uh, here based on the previous information here. Okay, so corresponding to any events A and B here, so this information which will be available to us here, correct? Similarly, okay, let us come to this point slightly later here. So this PA which is here and this PB at the denominator here, this is the associated probability corresponding to the event A and B here, correct? So this is information related to the events which is already available with us here, correct? So this information is already available with us here, and this information we generally called as a prior probabilities here. Based on the prior probabilities available with us here or known to us here, or this conditional probabilities, here we are trying to make a hypothesis to estimate what could be A given B here. Okay, so here I just try to understand, take an example. Okay, then it will be slightly clear to you. For example, if I am trying give some input to a system, okay, if I give an input to a system, then we will get some output, correct? This is my basic understanding. Corresponding to any system here, if I give some input here, then corresponding to that I will get an output. Okay, so you can think of that this A, so this A is your input and B is output here. So you can say A is your input, B is your output here. Okay, so what it states, corresponding to the input, you already have some information here, and what is the output form here, you already have some information about it based on the past experience. Okay, what are their associated probabilities, we could predict it here. Okay, and simultaneously we have also observed corresponding to a given input. If I say probability of B slash A here, means corresponding to a given input, I already know the output here. Did you get the point here? So I could correlate very easily here, right hand side here. Now try to think what is left side here. So this is A, we are trying to find out the input with respect to the given output here. Okay, at the first place corresponding to any system based on the given input, we have the idea about the output here. This is our basic understanding here, and simultaneously we also have the information about the source as well as the its corresponding outcome here. So you can say A and B, we also have the probabilities information. Now someone is asking or interested to find out corresponding to a given output, what could be the possible input here? Just try to understand here. We have not applied that input. We don't have any information that input or types of input here, nature of that input here. We are just interested to articulate what could be the possible output here. And based on that output, I'm trying to link it with input here. Okay. What is available? I'm going to repeat it again because this is very important aspects here. If you understand, then it will be very easy for you to further pick up here. So what we have done, we have taken the conditional probabilities. From the conditional probabilities, we have come to the equation this and the equation this here. And after the mathematical arrangement here, we have just slightly put the left hand side equal here, and we have equated the right hand side of this equations here. So when I'm equating this right hand side here, after arrangement here, what I have done, I have written probability of A given B will be equal to the probability of B given A multiplied with the probability A divided by the probability of B here. This is our understanding. And what we have defined, we have taken a system here. So corresponding to a system, there will be an input, and corresponding to that system, we are getting an output here. So what is happening? Based on the past information, we already have the probabilities information about the input and the output section. Means PA and PB is known prior information, and corresponding to a given input, I already have the uh, information about what could be the output here. This is also known to me. Now, we are interested to find out, articulate here, if I want or desire this output here, corresponding to this output, what could be the possible input here? So probability of A and B, whatever the assumptions we have taken, we are interested to find out A, that is the input corresponding to a given output here. This is totally a hypothesis here. This is not happen in actual here. Okay. So I hope my point is clear. Anyone has a doubt?
No, sir.
Okay. So if you understood this point here, so all the further discussion in the base theorem is going to be easy for you. I think some sound is coming from the Harshvardhan. Harshvardhan, you need to mute yourself. Okay. So here we are trying to find out posterior probabilities here based on the available prior probability information here. And in case of machine learning application, this is always a speculation or a hypothesis what could be in the future here. So just one example is given. If 0.01 of a population has schizophrenia, then the probability that the person drawn at random would have the schizophrenia is 0.01 here. This is a very rare probability here. It doesn't mean the person has the disease here. It is just in possibilities here. So what you have written, this could be written again in the just reverse form here. Probability of A given B, what we have just written, probability of A given B equal to probability of BA into multiplied by the probability of A divided by the probability of B. So this is the conditional probabilities, probability of given B. And here you could also think of another example. If you are trying to roll a total of 8 on 2 dice, if I'm going to roll a dice here, out of 1 to 6, any number could pop up on the top here. So what is the probability that you achieve this given that the first die rolled a 6 here? So one information, prior information is already known here. Here, what we are trying to find out corresponding to output. What would be output here? 2. What is its associated probabilities here? Correct. So we already have the prior information corresponding to the system as well as the one reference here. Okay. And based on that, we are trying to find out what could be the future here. This is just example. We'll solve some problem here. So okay. So let us take few things in the systematic ways here. Then we will solve some problem here. What we have discussed here till now, based on this equation, we talk about the prior probabilities associated here, and then left hand side, this one which we are interested to find P, probability of A for a given B, this is called as a posterior probabilities. Okay, so there are two terms here in the probabilities. One is prior probabilities, which information is already available with us based on the personal experience or observation here, or based on some experiments which we performed earlier here. Based on that, we already have some information here, and based on that, we have assigned some probabilities here. So this is the prior probabilities here. And second is the posterior probabilities, and this probabilities which we have written in the left hand side, a probability of A given B. This is not known. So based on the prior probabilities, we are trying to find out what could be the associated or the revised or the new probabilities here, and this is called as a posterior probabilities. And this is the fundamental use or application of Bayes theorem here in finding the posterior probabilities corresponding to the different practical problems here. And this finding the information practical problems here will give additional information here, and this additional information help us in making a correct decision here. Okay, so let us take one simple examples here, and then subsequently we'll move on nowadays. So as per the Bayes theorem, simple example here. So this is suppose that Bob is late one day here. His boss wishes to estimate the probability that he traveled to work that day by car here. So that person is late, and this is a probability associated with different mode of transportation associated here. So if his coming car is, the chances 50% late, bus 20%, train 1% here, and his boss actually doesn't know which mode of transportation has been used by the Bob here, and the boss has already assigned some prior probability of 1 in 3 in each of the three possibilities. It's 1 by 3. You have assigned all these three probability 1 by 3, 1 by 3, and 1 by 3 with equally likely assumptions here. And here, his objective is to find out that Bob is late as because he has traveled in the car here. It doesn't mean that Bob has traveled by the car here, but he is trying to find out what could be the associated probabilities here. The probability of A given B is equal to probability of B given A into probability of A into probability of B. This is our formulas which we are going to use here. Okay, so I think I got one of the response here. Good, very good. Oh, so Nishol, Satvik, Sridhar, Kamal, Vikal. Good. Okay, so let us understand here. So just we have mapped with our this problem statement with our mathematical understanding here. So as we are interested to find out that person is coming to the car and is already late here. It would be equal to a probability of being late if he comes to the car, probability of car, and divided by the probability that he is late here. Late means total aspects here. Probability if he is late here, if he is coming through the car here, it is 0.5. It is already decided here. Previous slide. This is 50%. If he is coming late here, this is the probability associated. And if he is coming through the car here, so as his boss assumptions 1 by 3 to all the mode of transportation, car, train, bus, so 1 by 3. If he is late here, so the associated probabilities here, what will be 1 by 3 into late with respect to the car, 0.2 with respect to the bus, 1 by 3, and 0.01 with the train, and 1 by 3 here. This is the probability that he will be late here, total late probability. So probability of car, his probability that he has come to the car, and as he is already late here. So we already know that person is late here. With respect to the given information, we are trying to find out here what could be the possibility that he traveled through the car. As we already know the information, Bob is late. Now we are trying to find out, as he always is late, what is the probability that he has selected the mode of transportation as a car here. So now substitute all this information in this formula, So probability of late if it's in the car here and multiplied by the probability of being in the car here. So 0.5 multiplied by 0.33 divided by probability of being late, and this being late is calculated here, so it will be divided by this whole number here. So if you solve it, it will get approximately 0.7042 here. So as many of you already given the correct answer here for this statement. This is one example here. Second example we are considering, there is a disease present in 0.5% population here, means 0.005, and blood test is 99% accurate, so it is 0.99, and false positive is 5% here, so it is 0.05. So even though we are saying the blood test is very much accurate here, but still there is some possibility it could give the false alarm here. So here if someone tests positive here, so what is the probability that they have the disease actually here? So just map it with our basic base formulas here. Probability of A given B is equal to probability of B given A, probability into multiply probability of A divided by the probability B. So here, what is the probability? Here we are interested to find out that the given a confirmed positive, what is the probability that person has the disease? Okay. Now it will be equal to the probability that person corresponding to a given disease, its associated positive probabilities multiplied by the probability of disease here and multiplied by the probability of being positive here, total positive possibility. So 0.99 into 0.05 divided by the total probabilities of disease, 0.99 into 0.05 and 0.05 into 0.995 here. Okay, false positive aspects here. So this, if you consider, if you go solve it here, so it will come to the 0.0905 chance here. There is just a 9% chance they have it. So still, it is a very rare chances for the occurrence. So still, just try to understand. This is all the data or hypothesis here. It doesn't mean that so many number of the population has gone for the test here. It is just a sample. Few person has gone for the test. Based on that information, we have drawn some associated probabilities here, and based on that probability, we are trying to map it with the mass level here. This is just an hypothesis. Actual number may be slightly varies. So now we are going for the one more example here, and with this you will have a more clear picture how this Bayes theory is going to help us in providing a clear picture, or Bayes theory is going to help you in taking a better decision here. Okay, so what we are doing, assume that a factory has two machines, and past record shows that the machine 1 produces 30% of items of output, and machine 2 produces 70% of the item here. So machine 1 30% of output, machine 2 70% of the output here. Further, 5% of the item produced by machine 1 were defective, and only 1% produced by the machine 2 were defective here. So need to be clear, machine 1 30% output share, machine 2 70% output share. Out of that, corresponding to the machine 1 5% defective items, and corresponding to the machine 2 1% defective items here. Okay, so if a defective item is drawn at random here, what is the probability that the defective item was produced by machine 1 or machine 2 here? So if randomly, if I'm going to draw a picture here, the item here, so what is the probability that it is defective? So let us define the events here, then we could go ahead. A1 is the event of drying an item produced by machine 1. A2 is the event of drying an item produced by machine 1 here. Okay, so just we have defined the two events, A1 and A2, corresponding to the two different events here. So if I'm going to pick an item, we are interested what is the probability that it is defective here. So just we have defined the two events, A1 and A2. And then from the first information, probability of A1 output share 30% means 0.3, probability of A2 70% means 0.7. From the additional information, as we have defined, B is the event of trying a defective item produced either by machine 1 or machine 2. So means probability of being a defective item selected from A1 here, it is 5%, 0.05, and it is probability corresponding to B, A2 here, it is 1%, means it will be, this is a mistake, it will be 0.01%. Okay, the required values are tabulated below here. Conditional probabilities here we may find out here. So without the additional information, we may be included to say that the defective item is drawn from machine 2 output, since it is equal to 70% here. There is the major chunk of output is coming from the machine 2 here. So we could say that chances for the defective item from machine 2 is more here. This is our first observation here. This is not accurate here. Okay. But once we solve it here, this mathematically here, then we will get the more clear picture here. So if we go for the joint probabilities here, then with the additional information we give a better picture if we calculate the defective probabilities here. So by machine 1 it is coming 0.682, and with respect to the machine 2 it is coming only 0.318 here. So we can say one is giving a 68% possibility that defective item is more likely drawn from the output produced by the machine 1 here compared to the machine 2 here. Even though machine 2 is producing taking a larger share in the output, and machine 1 is taking a small share in the output here. So this is just an information or inference we have drawn here once we have gone for the analysis here. Once we go for the analysis, we got these numbers here, and this number is going to give us clear picture here. And what is concluded mathematically, if we try to understand here, we could see with just one example here. If you are taking a 10,000 items here, just taking a 10,000 item produced, out of 10,000, 30%, 3,000 from machine 1, 7,000 from the machine 2, and as defective items from the machine 1 is 150 and defective items from the machine 2 is 70. So obviously we could say as the number of defective items from the machine 1 is more here, so the chances for this that item which we are going to pick it here is a defective, it belongs to machine 1, will be the more here. So this is another way to look this same problem statement. So why is Bayesian probability useful? It allows us to put the probabilities values on a known. We can make logical inference even regarding uncertain statement here. So there are some practice problem here. I am going to share this problem statement here with you all here. You need to practice these problems here. Okay. And one more thing, next week we'll have the small quiz in the next class Monday. Monday, once we meet here at 11:30 to 12:30 here, first we will go for the class. So maybe around 12 o'clock something, we'll go for the quiz here. And this quiz will be shared on the Google quiz, Google platform here. So you need to be ready for it. So corresponding to the unit 1, what we have discussed till today, this will be the part of that quiz here. Okay. So this will be okay. So I will share the slides here. You need not to worry about it here. I will share. And one more thing, I have shared the Google Classroom link with you all here, where I will keep on sharing the different information related to the course on this Google Classroom here. So you all need to join the Google Classroom here. All the information related to the course will be shared on this Google Classroom. Okay, many of you already joined here, but few I have still not joined it here. So for them, it is just a reminder. Okay, so with this, I assume yes. If any other questions here, you can ask. Otherwise, I will leave this. Any question?
Sir,
So one question is reference book here. So I could say you could go for the People's here. There's one reference book. It's very good book here. tables, you can go for it here. Or for the problem solving here, you can refer the SOM series book here. So a lot of good questions is given in the SOM series.
Sir?
Yes, quiz will be the objective multi-choice questions here. So more than one answer could also be correct here. If you give all the correct answer, you will get the marks here. Otherwise, you will not. Okay. So prepare thoroughly. Okay. So someone want to ask something?
Yes, sir.
Bolo.
Sir, sir, in the second last question, I could not understand the probability of positive people in the
Actually,
denominator.
I think we have time here. So maybe later on we can discuss it. Maybe next class here. Okay. I think
Okay.
I will share the slides here so you can understand. If you're not able to understand, we could discuss it here. No issue. Okay.
Okay.
Now it's time
Can
here.
you repeat the book's name once again?
I will share the complete details of the this textbook also here in the slides. Everything is available in that. No issue.
Okay, sir. Okay, sir.
Complete syllabus, everything is available. Need not to worry. Okay. Okay. Thank you.